Okay, welcome to week 10 of Violent Python. Tonight we're going to talk about covert communication using true color images and Python. I'm going to walk through that. So before I do that, I'm going to go ahead and do a quick demonstration or quick walkthrough of last week's assignment. Excuse me. And I'll try to go through that relatively quickly. I will post the solution for you tomorrow so you can walk through it as well. There's just a couple of fine points that I want to actually walk through to make sure that it's clear. So in this particular script, I gave you most of the setup for this back in the main section, and I gave you all of the lookups that you're going to need. But let's actually walk through this real quickly here so you can kind of see how this actually operates from the solution point of view. And we'll go ahead and just run this, and it's going to let me set a breakpoint here. It's going to ask me for the PCAP file that I want to process. I've got a couple right here in the same folder that I can access, so it's easier. One is called demo.pcap. They're the same ones you're using. I just wanted it to be more convenient so that it would be in the same folder for me. So as I kind of showed you last week, one of the nice things about the library that we're using, it allows us to iterate through the packets. And these packets are part of a PCAP file. So it has information in it like timestamps and all of the information regarding the packet. So we can, right from the PCAP file, I can get the timestamp so that I have that, and I have the time structure. So I know what hour of day this particular packet took place, which happened to be at the 0 hour. So based on that, we can start kind of moving down the protocol stack and actually up the protocol stack in order to get information. So I can start by getting the Ethernet frame, which is the lowest level packet that we're going to deal with. And in each one of these areas, I've shown you what is in the packets at each layer. So in this particular case, we're getting the Ethernet header. So I can get from the Ethernet packet, I can get the destination and source MAC address. And basically the MAC address is the hardware address of the Ethernet port that is connected to that particular computer. So I can get those. And because we have a lookup, I can actually go ahead and look up that just in case there happened to be information about that. For example, the manufacturer. Let's see if there was one for this. There was. It was a Raspberry Pi. And then I can also get the destination MAC, and I can perform that lookup, and I can get the manufacturer if there was one associated with that organizational unit, which it was VMware. This particular PCAP file came from Black Hat, or DEF CON. So based on that, remember this packet up here has the Ethernet type, sometimes referred to as the frame type, that we want to be able to get, because I want to know what type of frame is being carried by this particular packet. We'll only go through one of these to kind of show you. So in this case, we can process the frame type, and we've done a lookup to determine what the frame type of this was. In this case, the frame type was IPv4, a traditional IPv4 packet that can carry a bunch of different transports or protocols among it. So since it's an IPv4, this is what the structure of that. There's some very important information in this particular header of that packet. The source and destination IP address to start with, the protocol, the time to live. There's several key pieces of information here that we want to be able to gather. So in this particular case, I can go and I can get the IP packet, and I can get the time to live. And I can put my cursor over there, and that's the IP packet network address, big long number, and TCL is 64. So if this packet happened to go through 64 routers, it'll get thrown away because it's not able to transport that. But I can now convert the source IP address, that big number that we got, into something that is more like what we're normally used to seeing. 172, 116, 192, 33, 172, 116, 16, 192, 200. So those are the actual IP addresses that we have. So now we've got an IP address Now I wonder what the protocol is, in other words, that we're going to use. I know this is an IPv4 packet and it can carry several different transport protocols. The question is, which one is it? So I can get the protocol and that comes back from that as a number. In this case, it came back as 6. So I can then do the lookup to determine what 6 was. If I look at the transport, transport protocol 6 within the IPv4 header is TCP. So now I can process the TCP header. So we drop into the TCP. Now this is what the header of the TCP packet looks like. It has some additional useful information in it, like source port, a destination port, sequence number, acknowledgement number, checksum, a bunch of other things that we might be interested in. So in this case, I want to get the packet. And once I get the packet, 2 key pieces of information I'm looking for is the source and destination port. So I can get the source port, I can get the destination port, I can put my cursor over those, and those are going to be numbers, 502 and some really high number that's going to be a ephemeral port that is going to communicate with 502, which is a Modbus ICS protocol port. So I can go ahead and look up those descriptions, and if it wasn't, if the source port was there as 502, I can actually look at that, and now I can actually get the description of the port if it's available. So I can get the destination port description, which is ephemeral. I can get the source port description, which is Modbus. So those are things that I got from that by doing those lookups that I gave you that you could actually use. So now what I'm going to do is I'm going to create the key and the value for this particular observation. So in this case, we have the source MAC address, we got the destination MAC address, we got the source port, we got the destination port, and we got the protocol, in other words, the transport protocol, in this case, TCP. The value portion of the dictionary we're going to use is going to include the source IP, destination IP, the port descriptions, the manufacturers, if we have them, and the time to live. Now, those are the ones I chose that I wanted to capture. So now if I want to add this observation to the dictionary, at the top here, I created a couple of, way at the top, I created this IP object because I have a class that's going to handle this for me. So I have that IP object. It's an Internet Protocol object that I created. You'll see how that works in a second as I kind of walk through it. First thing I want to do is I want to add this new observation to my dictionary, which is being held by that object that I created, IP object. But I can step into it using the F7 key. And when I do that, I can see if this particular observation has been viewed before. If it has, I'm going to add to the hour count, in other words, how many times it occurred within that hour. If it doesn't, and in this case, it hasn't, because the first time through the loop, we're going to get an exception. So I'm going to set all of the hours list to 0 because we have not seen any observation yet except this one. And then I'm going to set the hour one, in this case 0 to 1 in order to be able to record that. And now I'm going to update my dictionary. So I've got this dictionary called Self Dictionary. I have this key that I'm going to use. And it has the MAC address, the port, the protocols, that kind of stuff, and then the hour list and the value. Notice the hour list now has 1 in the first value, and then we have value, which has all of the other information that I'm interested in. So I'm just keeping track of this, right? So now we've completed that update, but now I can actually update the port information that's related. So I'm creating a second dictionary that's going to allow me to keep information about the ports that are associated with this observation. So in this case, if the source port is not ephemeral, we're going to go ahead and I'll step into this too. This is the add port observation. That's part of this class that I created of IP observations. And I'm going to call that particular method within that object, no different than the methods that are in the objects that you guys have used before that come from the standards library. And I'm going to check to see if the key exists. It doesn't, obviously it's the first one. So now I'm going to actually update the port observation dictionary with the key and the description. So if I put my cursor over port observation, you notice that the key is the IP address. In this case, it was the source IP address, the port number, and the description of the port. So we have that information regarding that particular observation. We're also going to do the same thing for the observation of the destination IP address. So that can, the destination port, so we can actually do that. That's it. So this is how this works, and we do this for every single packet within there. Now, we've only processed, in this particular case, we had an IPv4 packet and a frame type of IPv4, and we happen to be TCP. We process TCP. The other protocol we can run into, or transport protocol we can run into, is UDP. It has a slightly different layout. There's a lot less information in the UDP port. It only has the source and destination port, but hey, that's what we were kind of looking for. Everything else here is pretty much the same as you just saw for TCP, and we're going to process it exactly the same. So we're going to call that add object. We're going to call the add port object for each one of the source and destination, so we can do that. The final transport type that we're going to deal with is ICMP. But you notice if we look at ICMP, there are no port numbers here. So that means when we actually define our key, we only have source MAC and destination MAC and ICMP as the protocol. We do not have the port numbers. And for the value, we have a source and destination IP address, but we don't have the port descriptions because there is no ports. And we do have the manufacturers if they're available and the TTL. So we can add that observation, right, from that perspective. The final thing is, you know, we were operating within the frame type of IPv4. I've processed one other frame type here called ARP, which is an address resolution packet, which basically helps to discover the MAC addresses of computers and technology that are running on our network. You notice this one only has source and destination MAC address. It doesn't even have an IP address, because the purpose of this particular protocol is to discover those IP addresses. And so all we have in this particular case to add to our object is the source and destination MAC, and that the protocol was ARP. And we have nothing here for source and destination IP address. We don't have anything for port descriptions, but we do have the source manufacturer and the destination manufacturer if they're available, and those can get added. So we do that for every one of the packets, and we just determine whether it was IPv4 or if it was ARP. And then for each one of those, if it was TCP or UDP, we update this object with that information. So we update the object with the information that we are observing. So they're basically calling an observing object that we have, that we've created. When we're all done, I'll set a breakpoint here. We do a little bit more work. This will take a second to process, because it's going to now run through all of the packets that were part of this. Remember, we were doing a loop here that was looping through every one of the packets here. I won't get to the top by the time it ends. But yeah, so it ended. So we process all of the packets that we have. But now we can actually print the IP observations. You notice that it's just another function or method that's associated with the IP object. Remember, the IP object has all the information here, and we've added to those dictionaries every time through the loop for each one of those packets. So now I can enter in here, and now it's going to basically go get a bunch of information from those observations that we have created. We're going to create our pretty table, and we're going to loop through our dictionary. Remember, we have a dictionary now that we've created with all of these values in it: source IP, destination IP, protocol, etc. And we're going to go through all of those in order to add those rows to our table in order to print it out. So we'll set a breakpoint down here. So everything happens inside the object because the object has all of the information about all the observations that we've made. So now I can print out our table. So the first table we print out is basically the IP observations that you've seen before. And we determine what protocol it was, ARP or TCP, and some UDP packets were here as well. And we can also print out our port observations. That was the second thing that we captured. So I can step through that code, which is a little simpler. All it's going to do is get the IP port and description and basically pull those together in order to be able to print out the result. So I'll continue with this, and I can print out our table. And now I have our table of IP observations. So, and they happen to be sorted by IP address. So all of the, so in this particular case, you could see that there were 3 ports that were observed for this particular IP address. For this particular IP address, there was also 3 ports observed. For this one, there were 3 ports. For this one, there was 3, and these last 2, there was 1 and 1. So those were those, and these are the descriptions that we looked up into those lookups that I provided you with. So that just kind of gives you a really quick walkthrough of my solution to this particular exercise, and I will post that tomorrow for you. And if you had any trouble with this, I would do what I just did and step through this code to basically make sure. And the important part about this is how each one of those observations is being stored in the dictionary. You've seen us use dictionaries here almost on every single assignment now. And you can kind of see the importance of being able to keep track of things within a dictionary because it has a key value pair. The difference here is the key can be complex. It can be not just a single value, but it can be, in our case, there were several values that were associated with the key, so we can define uniqueness and then keep track of the number of observations of that particular key that we have. And that gives us some useful information that we can print out. Okay, so in that particular case, the useful information is over here to the right, where we're keeping track of the number of occurrences of each one of those observations and how many times they occurred. So I know that looked like it ran fast, but you notice there were 6,903 ARP packets that happened in hour 0 and in hour 1, just in that particular example that was, based on those MAC addresses. So it gives us a lot of information as we start to capture this and record those observations during the hour of the day that they occurred. Now, you could set this up differently, and you could basically say, well, I'm only interested in if it happened during the week or in the weekend. You can obviously do that, since you can pick that particular timestamp and pull out that information and then record it any way you want to. But this one gives you that information. So with that, I want to kind of jump into this week's assignment, because I want to make sure that I have time to cover this. But if there's any questions regarding the last week's assignment, I certainly happy to answer them now, but also remember, you're going to get a chance to walk through that solution tomorrow once I post it for you, so that you can actually see how that operates. And it's very straightforward. It may seem really complicated, but as you start to store this information in dictionaries that hold that data for us, it's relatively straightforward. Any questions though? I always ask, are you guys still there? Can you hear me okay?
Yep.
Great, thanks. Okay, so we're going to talk about steganography, at least the simplest form of steganography that is out there. And I'm going to walk through a bunch of slides, and I'm going to give you a demonstration to kind of get you started with this week's assignment. So when we think about steganography, we're really talking about something that is called covert communications. So basically, the Department of Defense Orange Book, publicized back in 1985, basically defines covert communication as any communication channel that can be exploited by a process to transfer information in a manner that violates the system's security policy. So obviously, hiding information, let's say in an image or an audio file or a network protocol, would certainly violate the system security policy, because you're not supposed to do that, right? Everything should be, you should not be exploiting either images or protocols in order to exchange hidden information. So where did steganography come from? Where did the word come from for specifically? So steganography comes from the Greek roots of steganos, which equals covered, and graphy, which equals writing, yielding covered writing. I've been working on this problem for 20 plus years. So the first known uses of this were the early Greeks and Persians used several forms of covert communications in order to be able to communicate. The story of Demaratus is probably one of the most famous one. Demaratus was exiled in Persia, and while he was there, he received news that there was going to be an invasion of Greece. So he decided he wanted to get word back to Sparta in order to gain favor in order to come back, as he was exiled at the time. Since such an act of communicating that information would certainly mean death or worse, he wanted to come up with a way to secretly communicate that information. So he used the writing instrument of the day, which is a wax tablet. That's what this is, a kind of a description. You can kind of see the writing on the tablet and the stylus at the top that they use to engrave their notes. So it kind of looks like an iPad, but kind of an earlier version of that. And so what Demaratus decided to do was to peel back the wax from the tablet and engrave the message in the wood that he wanted to get back to Sparta. And he was able to sneak this particular tablet by the gates of the guarding the castle and get the message to Sparta. So it's the physical form of covered writing. That's where we believe the word came from. Word steganography came from this particular example of Demaratus, using the physical form of covering the writing of the secret message, in this case with wax. I created a slightly more modern definition of data hiding back in 1999 in one of the books that I wrote, and said the hiding of data within a digital carrier by slightly altering an insignificant characteristics of the carrier that does not appear to alter the normal rendering of the data. So it doesn't only apply, this definition doesn't only apply to images or movies or network protocols or anything. It basically talks about, hey, if I can modify an insignificant characteristic of what that object is that I'm exchanging to hide information, that would be kind of the goal of modern steganography. So why does steganography work? Well, one of the reasons it works when you're thinking about audio or video or images is it is the vulnerability that is being exploited is a human weakness. Now, certainly, there's more to it than that, so that there's ways to do this so that it's not able to be detected through other technical terms. But initially, it was basically, if you look at an image or a video, if you change pixels within an image in a slight way, we're not able to see the difference. And the reason is that we have poor detection and identification of differing shades of color, and certainly poor recognition of high intensity shades of color, bright blue, violet shades, etc. From a hearing perspective, we're very sensitive in our hearing to noise and distortion. However, imperceptible shifts in amplitude or phase, we're not able to pick up. So those are what are being attacked by making slight changes to color that we can't see the difference. And in the case of audio, changing the amplitude and phase shift slightly in order to be able to hide the information. So how does this work in digital images? That's what we're going to be talking about tonight. So images that are created either by software, digital camera, scanner, graphic software, whatever, are created. And each of these have pixels. In this case, on the right, you're seeing the simplest image that you could create. It's it only has white and black. It doesn't have any other color. So it is only a two color, in this particular case, image, black or white. So each pixel can only have the value of 1 or the value of 0. And then each row of the pixel defines how wide the image is, and the height defines how high the image is. So we measure that in pixels and sometimes in inches as well. But that's how it's made up. So true color images that we are used to seeing, are typically referred to as RGB images, or red, green, and blue. So each pixel within the image has 3 values associated with it. Now, there are different formats, but this is the most common. And so in this particular case, if we look at this first pixel, it has a value of red, green, and blue that have 8 bits associated with it. That means that we can set the value of red from 0 to 255 on the same thing for green and blue. So when we put those together, however, it gives us 2 to the 8th times 2 to the 8th times 2 to the 8th, or 16.7 million colors can be represented in a single pixel. So you're probably seeing why we're able to modify that single pixel in such a small way in order to be able to make changes. So if you look at a true color RGB image, we can basically take a look at making insignificant changes to, let's say, the least significant bit. In other words, if this value is a binary number from 0 to 255, if I change the least significant bit from 1 to 0 or 0 to 1, I'm only basically changing the value of that color red by one value. So very difficult to see the difference in that different shade of red, especially when it's combined with green and blue. So if we take a look at a true color BMP file, the one you're going to be using in this week's assignment, it has a fixed structure where there's a signature, and then there's the file length, and then finally there's a pointer that tells where the data starts. You're not going to have to worry about any of this, but I want to make sure you know how it works. We know what the width of the image is and the height of the image is, and the color density. In other words, this is hex, right? So it's 18, it's 24-bit color. So 8 bits of red, 8 bits of blue, 8 bits of green. Okay. So we get the color density. And finally, at that offset that was pointed to from here, this is where the data starts. And remember, there are 3 bytes per pixel: red, green, and blue. Those are the intensity values of red, green, and blue. So just to see if you guys are paying attention, if I have a pixel that has a red, green, and blue value of 0 for each one, red, green, and blue, what is the color of that particular pixel?
Black.
Correct, it's black, because there's no intensity of red, no intensity of green, and no intensity of blue, so then it is in fact black. On the other hand, if the red, green, and blue values were FF, FF, and FF, or 255, 255, 255, what is the color of the pixel then?
White.
White, exactly. And so everything in between that gives us the 16.7 million colors, okay? So again, we can make an alteration. If you notice these first colors here, 40, 20, 21, we could change them to 41, 21, 21. It would make a very slight change in that pixel. Okay, and since there are millions of pixels in a typical image, being able to find that slight variation is very difficult. To make the point, down here on the bottom, this is what 40, 20, 20 looks like, and this is what 41, 21, 21 looks like. And we're looking at thousands of pixels instead of one, just to kind of give you the point. So what I'm going to do next, I'm going to do this live, so I won't do it here. I'm going to give you a quick demonstration of how you actually can use the Python image library in order to be able to do this. So I provided you guys with a starter script, as I normally do, to kind of get you started on this week's assignment, so you can basically hide some data. So I'm going to start walking through this because I want to make sure I can get through this before the end of the hour. Sorry, the other script was still running. Okay. So I'm going to basically create a few constants here: red, green, and blue, 0, 1, and 2, just so we know which ones those are. And then what I'm going to do is I'm going to come down here and I'm going to use the Python image library to open this image of the Mona Lisa file that I have, the BMP true color BMP file. Then what I'm going to do is I'm going to use that image. This is the object that was created from that open call. And I'm going to basically get the pixels. So I'm going to get all of the pixels that are in that particular image into this array, basically, of that particular image. And then I'm going to set my current row and current value here. So now I'm going to get a pixel. So I'm going to use the pix to say, I want column 0, row 0 of that, and I want to know what that value is. So now I can actually look at the pixel, and you can see this is what that pixel is: 128, 96, 64. Those red, green, and blue values that are associated with that pixel. Pretty simple, right? So now we've got one pixel of that large image, and we have the red, green, and blue values. So I can extract the red, green, and blue values independently. So there's 128, 96, 64. So this is the first pixel of the image that we want to actually take a look at. So now I can print those out, and I'm going to print them out for you in binary because we're going to be working with binary. So in this case, the original pixels are 1 and all zeros, 0, 1, 1, and 5 zeros, 0, 1, and 6 zeros. So this is just a binary number that's basically the representation of that hex number or the decimal number that could range from 0 to 255. So what if I want to hide the value 0, 1, and 1 in this particular pixel? So I want to basically alter the least significant bit of each one of those in order to hide that. So I'm going to use one pixel, the red, green, and blue values, to hide the value 0, 1, 1 in them. So how would I do that? So I can say if the value of pixel 0 is equal to 0, then what do I have to do in order to make the alteration from my from the three values I want to hide? Well, in the case if it already exists as 0, I have to basically AND the value 1, 1, 1, 1, 1, 1, 1, and 0 with that, because I want to change that least significant bit to 0. It may already be 0, and that's okay. But if I want to make it a 0 for sure, I've got to basically perform a bitwise AND of that value. So move to the next one. If in this particular case, if the value of my list is 1, which it is in this particular case, it's 1, not 0. I want to basically change the least significant bit, whatever it is, I want to change it to a 1, right? I want to basically overwrite that least significant bit as a 1 because I'm using the 1 value that I want to hide now. And so in this particular case, it doesn't equal 0. It actually equals 1. So now what I'm going to do is I'm going to do a bitwise OR of that particular pixel value, the green pixel value, and I'm going to change it to make sure that the least significant bit value is going to be 1. Finally, I'm going to take a look at the third bit that I want to hide, which is also a 1. So in that particular case, I want to take the blue pixel and I want to make sure that the least significant bit value is 1. So based on that, I've made those changes. So now I can actually take a look at my red, green, and blue pixel values in comparison to what they started with. So now this is what the red, green, and blue value started with. And now I've hid the 0, 1, 1 in that particular pixel. So now I've made the alterations and it looks good. So now what do I do? Well, what I can do now is I can create a new pixel with the new red, green, and blue values. So when I do that, if I look at my pixel value, it's going to be 128, 97, 65. If you remember, it was 128, 96, 64. So now I've created a new value for that particular pixel. And now I can go back to my array, that pix array, that column and row, which was 0, 0, and I can assign that new pixel to that value. Once I do that, I could save it to a new file. So again, I'm using the image object and I'm going to save it to test Mona Lisa test BMP. And now I'm done. It's saved it out and the script is over. So that's your starter script. So I'm going to show you, well, before I show you the next part, I just want to kind of make sure there wasn't anything that was confusing about that. And I've provided you with the starter script so you can step through it yourself and you can change things. If you want to change what we're going to hide, if you want to change the pixel we're going to start with, you can do all that. But this gives you a starting point. Any questions so far?
I have one.
Okay.
What happens if your red value is 255? So binary wise, it's all ones, and you're trying to store a 1. You'll get an overflow if you, well, you're not adding, but you're
just going to, in that particular case, if you want to store a 1, you're going to do a bitwise and it's not going to overwrite it. This is one of the beauties of, you hit the nail on the head, was one of the beauties of hiding data within an image. Half of the bits are already going to be in the right state. So I'm not going to create an overflow because I'm just going to do an alteration. I'm going to basically modify that least significant bit. If it's already a 1 and I'm going to write a 1, it's going to be a 1. So I'm not going to change anything. So one of the cool things about least significant bit steganography is just what you hit on. If I have binary data that I'm going to hide in here, it's likely that half of the bits of the pixels that I'm going to alter are already going to be in the right state. So if I'm going to try to hide a 20,000 byte file, I'm only going to have to really change 10,000 because half of them are likely to be in the right state. So again, remember the bitwise AND is just basically altering. The same thing with the OR. Those are just altering the least significant bit. They're not, in fact, adding to it, for example. This is not an additive operation. It's basically just a bitwise AND and a bitwise OR. Really good question, though. Did that help a little bit?
Yes, absolutely. I was thinking, well, you're reading in. How do you know if that last bit is intentionally a 1? But you assume that every last bit is something you're going to read. So
correct. So let's take a look at, I'm going to show you the solution, then I'll talk to you about what you guys are going to do this week to kind of duplicate this solution. So I'm going to run my hide script, which is going to use the basic approach that I just showed you. Okay. And let me make sure I run that and show you what you're going to do. So I have mine a little fancier. I can do a linear or random placement. I'm going to just do linear for now. I could type. And so basically we could hide 7 different values in the least significant bit because we have 3 bits to work with, right? And so we could basically encode a message in that least significant bit. So the first message I want to hide to say, hey, this is a dead drop. So I'm going to say 0. And you notice that it's adding that dead drop in there. Then maybe I want to say, hey, the dead drop is going to occur at the, I don't know, the corner of Madison and 34th Street. I'm going to drop it in a gold garbage can. And I'm going to do that at 7 a.m. sharp. So now I've hidden this information within the pixels of the image by encoding those values 0 through 7. Okay, 0, 0, 0 through, and then 7 would be 1, 1, 1, right? And I basically hid those in different places within the image. So now I can select the message to hide. If I'm done, I don't have anything else to do. I can basically say at this point, hey, I'm going to use menu item 55 because I want to create a new image with this information I've identified. So we'll just call this test Mona linear. I'm gonna make this just say test Mona.bmp. And so it did that. It also came back and told me where, in other words, what column and row did I hide all of those values at? And I'm done. So now the trick is, okay, so now I've done that and I've created that. How would I get it back? That was one of the questions you were asking. So I'm going to select the covert file. What did I call that? Test Mona. My biggest problem. And it came back and said it recovered the message, dead drop, corner of Madison and 34th, dropped in a garbage pan, gold garbage pan at 7 a.m. sharp. Now you're thinking, how did you find that, right? How did you basically determine that that's where those were found? That's one of the tricks, but remember, you have the original Mona. So you know what the original looked like. So what you're looking for is any changes in any pixel in any one of the 3 values. And then you know that you have one, and then you can translate it. So that's the only hint I'll give you. So what you're going to do, see if I can go back to the briefing real quick. Oh, wrong thing. So this is your code book. This is what you're going to do. And you're going to basically do just what I did with my hide script and with the extract script. In other words, the hide and seek. You're going to basically hide information based on any one of these. Use a menu like I did or however you want to do it. And then basically hide this and then make sure that you can recover it. And the only thing that you need in order to recover it is the original image, right, which is the Mona that I'm giving you, and then the one that you created. If you have those two things, you'll be able to find the pixels that you've altered. Now, the only trick, and you asked a really important question, you don't want to hide something in an image in a pixel that is exactly the same as what you're trying to hide. So in other words, if the pixel is 0, 0, if the least significant bit of the pixel you're looking at is 0, 0, 0, and you're trying to hide 0, 0, 0, then you're never going to be able to find it, right? So you got to make sure that when you hide something in one of the pixels, at least one of the least significant bits is going to change so that you're able to find that because you have the original image. So that's the fun you're going to have this week. You'll be able to use the starter script. It gives you a lot of, play with that and make sure you understand how that works. Change a bunch of things like I mentioned. You could come here and you could change. Let me go back to the starter script. You could come back here and you could change a couple of things here. You could change what 3 values I want to change. And you could also pick a different column and row that you want to change them in. So you have a couple of things you could come in here and play around with. I set the row and column to 0, 0, but you could set them to something else. And then basically hide some things and see if, just to see how that works. And then once you got a really good understanding of how the starter script works, then your challenge is, how do I basically encode these secret messages, that have a value of 0, 0, 0 or 0, 0, 1, 0, 1, 0, all the way to 1, 1, 1, within those pixels. So we're limited to 7, actually 8 messages that I can hide, but we can have those messages mean anything we want. Any questions? Hopefully you're going to have some fun with this. Everybody seems to really like this particular challenge. And so play around with it for a couple of days. And then if you have issues, then we can certainly talk about them during the tutoring session on Saturday and obviously in the office hours on Monday. But any questions? Either everybody thinks this is too easy or everybody thinks this is crazy. I'm not sure which one.
Oh, it's a lot to take in. That's where I'm at for sure. So there's definitely a lot there, but
Yeah.
It looks cool.
Okay. Yeah, have fun with this. Like I said, this is really a fun exercise this week and you can do a lot with it. And then next week, I'll talk to you a little bit about other things that we could do like this to hide information within a true color image like this. But like I said, get started on it as soon as you can. So if you have questions, you can come to the tutoring session on Saturday or in the office hour on Monday so we can clear up anything that you may be running into. But you have enough here to do that, to basically make the modifications. Remember, the only tricks here is that once you create those new pixels, you got to write them back to the row and column that you want to alter. And then when you're all done with all of your changes, you're going to use the image.save method that's part of, remember, we created this image object that allowed us to load in the pixels, to retrieve a pixel, to modify a pixel, and then to create a new pixel, and then to be able to write it back to that pixel and then save it out. So all of that is part of the Python image library, which is in the VLE for you. If you're not using the VLE, then you have to install the Python image library within your desktop version of Python. Okay. Any final questions?
I did have a question.
Yeah, sure.
So the only reason we know what the modified bit translates to is because we have the code book, right? There's no actual data being stored in that bit.
That is correct.
Okay.
And so what that does is hit the nail right on the head. What that does for us is that if you take this farther and we had a larger code book that we were hiding information, let's say in multiple pixels or whatever, we can change the code book anytime we want, right? So even if somebody detects the fact that we've altered some of these pixels, they still don't know what the message is. They just know that there is a message, right? So remember the whole concept behind steganography and how it's different from encryption is the fact that in encryption, you're basically, everybody knows it's an encrypted file, right? There's no hiding the fact that it was encrypted, but only people that have the key can recover the data that was in that particular file. The whole point of steganography is to hide the mere existence of the message, and then also make it difficult to translate what the message is, even if you can detect the existence of the message. So the whole concept of hidden in plain sight, in order to be able to do that. But again, going back to your comment, if you didn't have the original Mona Lisa, right, how would you detect that there were pixels altered? So how would you even detect that? There's some statistical things that we can do, but it's really hard depending upon the size of the message that you're trying to hide in that particular case. So using a code book in combination with hiding as little as you have to in order to be able to provide the message. And as long as the someone trying to analyze this doesn't have both the code book or the original image, then it would be very difficult to even discover it. But even if they were able to discover it, they wouldn't be able to translate what the message meant. Make sense?
Yeah, thank you.
Yeah, you're welcome. Great question. Great question. We're trying to not conceal what the message is by encoding it, in this case, in 3 simple bits. So in order to be able to do that. So these messages can mean anything you want. It doesn't have to mean these things. It could mean something else. It's your translation. It's your code book.
Did you say that you needed the original image and the altered image in order to extract the message?
That is correct.
Okay. So you can't predetermine like an algorithm of where in the file you would store it, and then give that to another script and have that apply the exact same algorithm to find the pixels that had been updated.
Right. In this particular example, there are other algorithms that I've developed and others developed that basically all of the information is only in the altered image. And if you have the key, you can then basically recover the actual message. But in our case, the simple form of this, you have to have both the original and the altered in order to be able to extract the hidden content.
Perfect. Thank you.
Welcome. All right, well, have some fun with this week, and I will post this video and the solution to week 9. One point, for whatever reason, I never enabled the quiz for week 9. I did that today, and I made it due next Wednesday. So make sure you go back and do the week 9 quiz. It is not hard. I just must have forgot to enable that particular quiz item. I thought I had, but it was still hidden from you guys. So go back to week 9 when you get a chance and make sure that you take the quiz. Like I said, it's not hard. And I'm giving you another week to basically do it.
It was available, I took it last week.
Really? Because
Yeah.
I went there today and I looked today, and for whatever reason, my system was showing it was hidden. And I swore that I basically enabled it, but I don't know what happened. Maybe there's something wrong with my view of the system. But anyway, it's enabled now, and I did make it available and make the due date next Wednesday, just in case anybody missed it. Well, thanks for that feedback, because I looked from my machine's perspective, it wasn't enabled for some reason. All right, well, listen, everybody have a great rest of the week. Be safe, and look forward to seeing you on Saturday or Monday, and have fun with this, and we'll see you soon. Have a good night.
Thanks a lot. Bye.
Bye.